kids, welcome to the second part of your Chapter 10 or Chapter 9 review sheet. We're on the section on page 510, numbers 66 through 72. We are finding all solutions. That includes real and imaginary. So here we go. We have an equation given to us right here. Notice we have all the terms on one side, so we're ready to factor. Unfortunately, it's a 5-term expression. We cannot factor that. So in order to find the zeros, and why am I trying to find the zeros? Because the right side over here is equal to 0. So I'm going to have to list out my possible rational zeros, get a list of numbers, and start testing them, okay? So my lead coefficient is 1. My constant term is 2. Don't worry about the sign. The factors of 1 would be 1. The factors of 2 is 1 and 2. So you put 1 over 1 and 2 over 1. So 1 over 1 is 1, 2 over 1 is 2. Be sure and put plus minus in front of each number. So I have 4 numbers. Now listen, if there are any rational answers to this equation, they will be in this list, period. So I'm going to start with the number 1 and check it. 4, 3, 2, 1, constant term, so we're good there. My lead coefficient is 1. Next coefficient is 1. Next coefficient is negative 1. Next coefficient is 1. Next coefficient is negative 2. I have 5 numbers. My degree is 4. 4 plus 1 is 5, so I'm good. Bring down this. 1 times 1 is 1. Combine. 1 times 2 is 2. Combine. 1 times 1 is 1. Combine. 1 times 2 is 2. Combine. Look at that. Good deal. So 1 is a 0, or it's one of my answers. I start off with an x to the 4th, so now I have x cubed, x squared, x, and my constant term. They're all positive. You know what, guys? That's a 4-term expression. I think I can factor it. In fact, I know I can, so I'm good. I'm going to erase all of this. I don't need it anymore. I can factor this thing, so here we go. It's a 4-term, it's a quadnomial, so pull out what's common. The first 2, that's x squared, and you're left with x plus 2. Pull out what's common here, which is a positive 1, and you're left with x plus 2. Write your matching parentheses once. Your other parentheses is x squared positive 1. Now, on this first problem, I will set these parentheses equal to 0 and solve. For the rest of these problems, I'm not going to do that, okay? Because you guys are big Algebra 2 students. You should have no problem taking each group, setting equal to 0 and solve. But I will do it on the first problem for you. X plus 2 equals 0. Bring the 2 over, make it negative. X equals negative 2. X squared plus 1 equals 0. Bring the 1 over and make it a negative 1. Now take the square root of both sides. The square root of x squared is x. The square root of negative 1 is positive negative square root of negative 1. However, I'm going to have to make this positive and put an I on the outside. And the square root of 1 is 1. So I really have positive negative 1i, or just I. So there we go. Here's one answer. Here's the next answer. Here's the next answer. And it should match these right here. Okay? And it does. 67. Alright, now look. I'm solving this equation. I have 4 terms over here, all set equal to 0. I might be able to factor this. Let's see. Pull out what's common in the first 2, and you're left with x minus 1. Pull out what's common in the next 2 terms, 16, and you're left with x minus 1. Look at that. Pretty easy. So your factorization is x negative 1 and x squared positive 16. Look at that, doing good. So take this parentheses here, set it equal to 0 and solve, and you'll get 1. Take this parentheses, set it equal to 0 and solve, and you'll get this right here. Okay, there we go. Let's check and make sure we didn't make any mistakes anywhere, and we are good. Number 68. Hey, once again, guys, we're really doing pretty good here. I mean, we have a 4-term expression all set equal to 0, so we can at least try to factor this, okay? If you pull out what's common in the second two terms, that's a positive 1. And you're left with 2x negative 3. Now we can definitely factor this because the two parentheses match. So write your matching parentheses once. And the other parentheses will be x squared positive 1. So if you take this parentheses, set it equal to 0 and solve, you'll get 3 halves. If you take this parentheses here, set it equal to 0 and solve, you'll get positive 1, positive negative 1i, or just positive negative I. And that is the answer. Number 69. Okay, now we have a 5-term expression, so we cannot factor it. Make sure it's equal to 0. If it's not, you'd have to take care of that, okay? But it is equal to 0, so we're good. Now, we have to list out our possible rational zeros. My lead coefficient is 1. And my constant term is negative 12. We're doing this because, students, we cannot factor it. So we're going to have to find one of the zeros to help us. So the factors of 1 would be 1. The factors of 12 would be 1, 12, 2, 6, 3, 4. Put each of these over 1 and you get positive negative 1, positive negative 12, positive negative 2, positive negative 6, positive negative 3, positive negative 4. There's your list of possible rational zeros. If there are any rational zeros or rational expressions for this equation, they will be in this list. They will be in this list, excuse me. So I'm going to start checking these numbers for zeros. So here we go. I'm going to try positive 1 first. I always start with my smallest numbers and work my way up. So here we go. I've got a 4, 3, 2, 1 constant term. So I'm not missing any numbers. So I've got a 1, then 2's a coefficient, then 1's a coefficient, then 8's a coefficient, then negative 12. Count your numbers. 5, 4 plus 1 is 5. Everything's good. 1 times 1 is 1. Combine. 1 times 3 is 3. Combine. 1 times 4 is 4. Combine. 1 times 12 is 12. Combine. So I'm left with 1x cubed, 1 less than x to the 4th, positive 3x squared, positive 4x, positive 12. Now maybe that's factorable, maybe it's not. Let's see if it is, okay? Let's take this 4-term expression, pull out what's common in the first two terms, and we're left with x positive 3. Pull out what's common in these last two terms, that's 4, and you're left with x positive 3. So yes, it is factorable. So I'm going to erase all of this. I don't need any of this. Oh, I do need that actually. I found one of my answers was what? 1 gave me out a 0. That's one of my answers. So I'll put it up here before I erase all this. And here we go. So now to finish the factorization, write your matching parentheses once. And we're left over with x squared positive 4. Now, if you take this parentheses, set it equal to 0 and solve, you'll get negative 3. Take this parentheses, set it equal to 0 and solve, and you'll get this right here. So I have 1, 2, 3, 4 answers, and that makes sense because I have a degree of 4. I can have no more than 4 answers. Negative 3, positive 1, positive negative 2i. So we're doing good. Moving on to number 70. Okay, once again, I have a 5-term expression, so I cannot factor it. It is set equal to 0. That's good. Let's list out my possible rational zeros. Lead coefficient of 1. Lead coefficient of 9. The factors of 1 would be 1. Factors of 9 would be 1, 9. 3 and 3. We'll put the 3 ones. Put all of these numbers on top of this number over here. So 1 over 1 is 1. 9 over 1 is 9. 3 over 1 is 3. So we have 6 numbers that we might have to test. If any rational zeros or rational answers exist, they will be in this in this list of numbers. All right. And so here we go. Let's test positive 1 first. When I write down my coefficients, let's see if we're missing any terms. 4, 3, 2, 1, constant term. And so I have a coefficient of 1, negative 8, negative 8, negative 8, negative 9. I have 5 numbers with a degree of 4. That's good. Bring down my 1. 1 times 1 is 1. Combine. 1 times negative 7 is negative 7, combine. 1 times negative 15 is negative 15, combine. We're not going to get a 0, guys. So, no, we're good there, okay? Let's go ahead and test a negative 1 and see if that works. So here we go. Bring down your 1, negative 1 times 1, negative 1, combine. Negative 1 times negative 9, positive 9, combine. Negative 1 times 1, negative 1, combine. Negative 1 times negative 9, 9. So that's good. That's good. Negative 1 is one of my zeros. Now I did have a 4th degree, so I'm going to make this a 3rd degree. Negative 9x squared, positive 1x, negative 9. So that's my new expression I'm going to use now. And I'm pretty sure that's factorable. But let's make sure that it is. Pull out what's common in your first two terms, and you're left with x negative 9. Pull out what's common in your last two terms, that would be a 1, and you're left with x negative 9. So yes, it is factorable, so we do not need any of this. Let's pull this up here. And here we go, let's finish factoring it. Write your matching parentheses once. And your other parentheses would be x squared positive 1. Now, take this parentheses, set it equal to 0 and solve, and you'll get 9. Take this parentheses, set it equal to 0 and solve, and you'll get positive negative 1i or I. So we have 4 answers. Let's see if they match here. And yes, they do. Moving on to 71. Okay, notice I have the right side equal to 0, which is good. I have 5 terms, so I cannot factor it. So let's list out my possible rational zeros. I have a lead coefficient of 2 and a constant term of 3. The factors of 2 are 1 and 2. The factors of 3 are 1 and 3. So we take each of these numbers and put them over these numbers here. So 1 over 1 is 1. 1 over 2 is 1 half. 3 over 1 is 3. 3 over 2 is 3 halves. And we're finished. If any rational zeros exist, they will be in that list of numbers right there. So now we've got to test these. Alright? So here we go. I'm going to start with my smaller numbers first, the number 1. And let's see if I'm missing any terms. I've got a 4, 3, 2, 1, constant term. That's good. My coefficients are 2, negative 3, positive 7, negative 9, positive 3. I have a 4th degree and 5 numbers. That's good. Bring down your 2. 1 times 2 is 2. Combine. 1 times negative 1 is negative 1. Combine. 1 times 6 is 6. Combine. 1 times negative 3 is negative 3. Combine. So there we go. I have an x to the 4th, so I'm left with 2x cubed minus 1x squared, positive 6x, negative 3. Okay, now maybe this is factorable, maybe it's not. Let's see, okay? Pull out what's common in your first two terms. That's an x squared. And you're left with 2x minus 1, or negative 1. Here, pull out a 3. It'll be positive because we have a positive sign here. And you're left with 2x negative 1. So it's definitely factorable. Our parentheses match. So we do not need any of this, okay? Except, don't forget, that one of our answers was already a 1. Let's put that answer up here. I almost forgot to do that again. You gotta be careful not to do that. Now I'm gonna pull this up. Write the matching parentheses one time. And then write the other parentheses, x squared positive 3. And here we go. If you take this parentheses, set it equal to 0 and solve, you'll get 1 half. If you take this parentheses, set it equal to 0 and solve, you'll get positive negative square root of negative 3. And of course that negative 3 can become positive if you put an I right here. So there's your 4 answers. I think they might put their I in front of the radical, which is fine. I like putting mine here at the end. Either way is fine, okay? Alright, moving on to number 72. Now notice on this problem, we do not have the right side equal to 0. Don't ever forget to check that, guys. Your kid doesn't know good to factor or find the zeros if the right side's not, if one of the sides are not equal to 0, okay? So bring that 2 make it a negative 2. There we go. Now, I have a 4-term expression. Maybe it's factorable, maybe it's not. Let's see. Pull out what's common in the first 2 terms, and you're left with this. Pull out what's common in the second 2 terms, and you're left with this. Yep, the parentheses match, don't they? So we can definitely factor it. So my factorization is 3x negative 2, x squared positive 1. Now, take this first parenthesis, set it equal to 0, and solve, and you'll get 2/3. Take this parenthesis, set it equal to 0, and solve, and you'll get this right here. If you put the 1 in front of the I, that's no problem. It's totally up to you, okay? And here is the answer. Exact same thing, okay? Alright, moving on to the word problem, number 73. Now, if you'll listen carefully, I can really explain it, but you gotta listen, okay? From 1980 to 1990, the number of grocery stores in America is this. So you put in a year, and I can tell you how many grocery stores there were in America. The average sales of each store can be modeled by this. Okay? Now think about if I told you there were 20 stores in Chattanooga, and each store averaged $1 million in sales. How would you find the total sales? Well, you would take 20 times a million, because each store averages $1 million, and there's 20 stores. That really should make sense, guys. Each store averages $1 million, there's 20 stores, multiply them together. Well, guys, it's the same thing here, look. I have my total number of stores right here. Sorry about that. I have my total number of stores right here. And I have the average sales per store right here. So if I take this part of the function here, which is what I have right here, times this function here, which is what I have right here, then I have my function. There it is. I mean, think about it, guys. I have total number of grocery stores times each store's average sales. That gives me the total amount of sales in America. Then it says approximate the model, or use the model to approximate the total sales in 1988. So now let's go back up here. T equals 0 represents 1980. 0 represents 1980. So 8 years later, that's represented by the number 8. So everywhere there's a T, you're going to put 8. And then do all your simplifying, and you will get this right here. Okay? That's just all calculator work. And that's it, guys. These are not meant to be difficult word problems. Let's take a look at number 74. Okay, students, number 75, another word problem. It's actually pretty simple, guys. Let me explain this to you. And I think you'll be fine with this. From 1970 to 1990, the total amount spent in advertising is represented by this. Now, when it says the total amount spent advertising, it means locally and nationally. Let me explain the difference, okay? If you're watching TV, you might see a commercial. That's a national commercial, okay? It's for maybe Chevrolet cars, or anything like that's a national chain, a Walmart commercial or something like that. But a local commercial would be a commercial that airs on your television that is advertising a local business, not a national business, but a local. So here's what we have. We have a model right here that gives the total amount of dollars spent on advertising in the United States, whether it was a national commercial or whether it was a local commercial. Got it? That's the total. Now this model here shows you the amount spent on local advertising. Got it? So this model here is the total amount spent on local. They want you to write a model that shows the amount spent on national. Well, guys, that should be so easy. If you know the total amount spent in the country and you subtract out the local amount, what you're left over with has to be the national amount of spending. And that's exactly what we have. This model right here is my total amount spent in America on all advertising, national and local. Okay? From 1970 to 1990. left over with has to be the national. It has to be a model that represents the national. Alright? Now, I'm trying to see sort of how this work if I have the answer close by, and I do. It's right here actually. So the answer would be I'm going to use the letter N for national. Well, actually, they tell you to use the letter N right here. If you subtract, you will get this right here: 143 t squared plus 582t plus 10,650. So there's my model. Then it says, use the model to approximate the amount spent on national advertising in 1986. Now, 0 represents 1970. So 10 would represent 1980. So 16 would equal 1986. So everywhere there's a T, you're going to put 16. And if you'll do that with a calculator, you will get out the correct answer, which is 56,570. 56,570. That's million, because it says all of your models were already in millions of dollars. See that? All of your models were already in millions of dollars. So when you get this number out, you put the word millions after it. And that's how much money was spent in 1986 on national commercials. Okay? National. Now this next word problem is going to be pretty challenging. I look forward to doing this one, okay? On April 30, 1989, Benjamin P. Field opened a box that had been in his family since 1889, so 100 years. His father told him that the box had been sealed on April 30th, 1889, and that it contained memorabilia of the centennial of George Washington's first inaugural. The box had a volume of 2,280 cubic inches. Now, let's stop right there, okay? The volume of a box is what? Do you remember? It's length times the width times the height, okay? So, we already know the volume, of course. The volume of the box is 2,280, alright? Now, they tell us the box's dimensions. Now, I know, students, that we don't know which one's the length and which one's the width and which one's the height, and I really don't care, because you're multiplying all three anyway, so who cares, you know? But here's the deal. They want us to find out what x is. They want us to solve for x, so I've got to come up with an equation to solve for x. So I have my volume equals length times width times height. That is a true, accurate model. So I'm going to substitute this in for the volume. For the length, I'm going to go ahead and put 5x. For the width, I'm going to go ahead and put 2x plus 1. Actually, you know what I'm going to put? I'm going to go ahead and do this. I'm going to put 2x plus 2. Little shortcut there, because 2 times x is 2x, 2 times 1 is 2x. So off to the side I have a 5x, and I have a 2x plus 2, and I have a 6x plus 1. Those are my dimensions. I'm not sure which one's my length, width, and height, okay? So right here I'm going to put 6x plus 1. So there we go. I have my length times my width times my height. Now, this is going to be a little bit of a pain. They want us to solve for x. Now relax, guys. It's not as hard as it looks, okay? I'm going to get rid of this here. You can look in your book. You can look in your book to look back at this problem if you need to. I need some more room, so I'm going to get rid of this. Now, let's pull this up here. Now, I'm asking you to solve this equation, and you should be able to, guys. You know what to do. First of all, you want to simplify this side over here. So 5x times this parentheses would be 10x squared. Positive 10x. Now keep parentheses around that because it's this whole thing times this right here. There we go. Okay, got it. 5x times 2x, 10x squared. 5x times 2, 10x. Now, bring down your 6x plus 1. Now take your 10x squared and multiply it through. 10x squared times 6x, that's 60x cubed. 10x squared times 1, that's 10x squared. 10x times 6x, that's 60x squared. And 10x times 1 is 10x. And over here we still have 2,280. Now, obviously, since we have a third degree polynomial function, we would like to factor it. But I've told you guys over and over, never ever factor unless one of the sides is equal to 0. So I'm going to bring this 2280 over and make it negative. So I finally have this 60x cubed positive 70x squared, 10 plus 60, positive 10x, positive 2000, or negative, excuse me, be a negative because we're going to bring it over from the other side, negative 2280. So my young math scholars, this is what we're trying to solve right here. So I can get rid of all of this now and bring this up here and get to work on it. Now, we just did a bunch of these, didn't we? Way back here. We solved a bunch of these, right? Sure we did. So here we go. First of all, we would like to, I'll tell you what, first of all, pull out what's common. You can take a 10 out of everything. So if you pull a 10 out, you're left with 6x cubed, positive 7x squared, positive 1x, negative 2,200, or 200, excuse me, negative 228. Now, I'd like to factor this four-term expression, but trust me, if you try to factor it the way I've taught you, it's not factorable. So we're going to have to list out all the possible rational zeros. Now, I understand if you're listing out all of the factors of 228 and 6, that's crazy. I get that, okay? We're trying to find the zeros for this right here, and I would never give you a problem like that on the test, alright? But I want to go ahead and tell you one thing you could do is type this entire expression right here into your grapher. Are you listening? I've got some great advice for you. You could type this entire expression right here into your grapher. Got it? And then hit graph. Because remember, x-intercepts are the same thing as zeros. So that's what I typed this whole thing into my grapher. I hit graph, and I saw the graph cross the x-axis at 3. Right here, 1, 2, 3. It goes right through 3. So I said to myself, okay, one of my zeros must be 3. So I brought down my four-term expression here. And I put the number 3 here. And I wrote my coefficients, 6, 7, 1, negative 228. Bring down my 6, multiply, combine, multiply, combine, and 3 times 76 is 228. So it works. I got out a 0. So now I'm left with 6x squared, because I had a third power here. 6x squared plus 25x plus 76. Okay? So I'm going to grab this right here. Maybe this is factorable too. Maybe I'll get out more than one answer. I have one answer so far, 3. I'm going to pull that up here. I have one answer so far, 3. Now maybe this expression is factorable. Maybe it's not. Alright, let's see. And actually, to be honest with you, hopefully you're taking notes. I don't need this anymore up here. I'm going to go and get rid of it too. Now you're saying, Mr. Error, why did you not list out all the possible rational zeros? Guys, are you serious? Look at these numbers I would have. I have a 6 and a 228. That list would be huge. So that's why I decided to use my graphing calculator to help me. Now, those of you that do not have a graphing calculator, I would never give you one test or a quiz that had such big numbers that you could not use listing out your possible rational zeros. Okay? Now, I could try to factor this, but it's going to be a lot of work. Remember, I have to take my 6 times my 76. That gives me, I think, 456. So I want two numbers multiplied to give me this. When I add together, give me 25. That's going to be a lot of work. So I think I'm going to employ my graphing calculator again. And I'm going to type in my calculator this model right here. 6x squared plus 25x plus 76, and hit graph. And actually that might not be a good idea because the numbers are so big it might not show up on my screen. So I'll tell you what, I'm going to go ahead and see if this has these zeros by using the quadratic formula. That's what I'm going to do because it is a quadratic. I can do that. So negative b plus minus the square root using the graphing calculator was not the best idea. So negative b plus minus the square root of b squared, that's 625, minus 4a times c. 6 times 76 gives me 456. And then all over 2 times 1, which is 12. So now I have negative 25. Positive negative the square root of 169 all over 12. And the square root of 169 is 13. So now I have negative 25. Positive negative or plus minus the square root of 13 all over 12. So now let's break this down. Negative 25 plus 13 would be negative 12 over 12, which is negative 1. And then negative 12 minus 13 would be negative 38 over 12, which I'm not sure exactly what that gives me, but it gives me a negative number. A negative number. You know why I don't really care? Because look up here, guys. I cannot have a negative number for my answer. So these two answers aren't going to help me. Negative 1 doesn't help, and a negative number doesn't help. Why don't they help, Mr. Arrow? Because look, one dimension was 5x. So if one dimension is 5x and you put a negative number in like negative 1, that means you're going to get out a length or a width or a height of negative 5. That's impossible. That can't happen. So negative numbers will not work. Now, are negative numbers solutions to this equation? Yes, definitely. But since it's a word problem, all the answers might not help. Okay? So negative numbers don't help. Negative numbers don't help. This is the only one that's going to help. So my first answer is, they said to solve for x. There's what x equals. The next thing they want you to do in this word problem is to find the dimensions. So put a 3 in here and you get 15 inches. Because it said earlier in the problem that these dimensions here are in inches. Put a 3 right here. 2 times 3 is 6 plus 2 is 8. And then put a 2 right here. You'd have 12 plus 1 is 13. So now you know the dimensions of the box. It's 15 inches by 8 inches by 13 inches. And there we go. Pretty challenging problem, guys, but a really good thinking problem. Would I give you one like this on a test? Yeah, I probably would. I mean, I'm not saying I will, but I wouldn't hesitate to do that. Just not as big of numbers as this problem had. Okay, last problem. We're going to factor this into linear factors, okay? So that means we want every parentheses to have a, excuse me, to have a power of 1. Every parentheses should have x to the power of 1. So let's see how we do, okay? First of all, we can't factor this as 5 terms. So let's find some zeros. Bring down your 1, your 8. Factor this is 1. Factor would be 1, 8, 2, and 4. Put each of those over 1, and you'll get positive negative 1, positive negative 8, positive negative 2, positive negative 4. So there's my list of possible rational zeros. If any rational zeros exist for this expression, they will be in this list, okay? Now, I'm not sure. I don't have the answers in front of me. Let's go ahead and see if 1 works. So I'll put a 1 here, and I'm not missing any terms. 4, 3, 2, 1, constant term. So my coefficients would be 1, 3, negative 2, negative 12, negative 8. So let's see if 1 works. Bring down your 1. 1 times 1 is 1, combine. 1 times 4 is 4, combine. 1 times 2 is 2, combine. And we're not going to get a 0, so we're going to go on and check negative 1. Here we go. Negative 1 times 1 is negative 1, combine. Negative 1 times 2 is negative 2, combine. Negative 1 times negative 4 is positive 4, combine. Negative 1 times negative 8 is 8, combine. 0, good. So there's 1 answer right there. So now I'm left with this. X to the third, positive 2x squared, negative 4x minus 8. Now let's see if this is factorable. Okay, if it is, we're doing good. So, pull out what's common in your first 2 terms and you're left with this. Pull out what's common in your second 2 terms. 4. It'll be negative because this term's negative. and you're left with, well, let's see what you're left with. Let's try x plus 2. I put x plus 2 because that's what I had over here. Negative 4 times x, negative 4x, negative 4 times 2, negative 8. We're good. Okay? So now I have, for my factorization, x positive 2, x squared negative 4. Okay? Now, let's erase all of this. Don't forget I have 1, 0 at negative 1. Let's not forget that, okay? So here's what I have. I'm not finished, first of all, because I haven't taken care of this 0 over here. If I have a 0 at negative 1, that means one of my linear factors. You remember how to do this? One of my linear factors would be not x minus 1, but x positive 1. You change the sign. So if negative 1 is one of my zeros, then one of your factors is x positive 1. Now, this x has a power of 1. That's good. Check. This parentheses has a power of 1. Check. But this one has a power of 2. So we've got to factor this further. Now, we have perfect squares here. The first term is positive. The second term is negative. So we could factor this. The square root of x squared is x. The square root of 4 is 2. Make one positive, make one negative. There we go. And then bring down your other two parentheses. And we're finished. Now here's the thing. You are finished, okay? Very good. All of these x's have a power of 1, so you have factored this all the way down into linear factors. But I have a question for you. So we're finished. This is your answer. Okay, that's good. Now I've got a question for you. What if, when you factored this thing out, you had a positive 4 here? It's not factorable. So how can you break it down to linear factors? Well, in that case, if that happens on the test, you come over here, set it equal to 0, and solve. To find the zeros for that parentheses, take the square root of both sides and you'll get this right here. Positive negative 2i. So now think about it. I know this parentheses is x positive 1. I know this parentheses is x positive 2. Now, I have two more zeros here. So I would have x, I have a positive 2i, so x negative 2i. And then I have a negative 2i for a 0, so I change the sign, x positive 2i. And there we go. So even though this wasn't factorable with rational numbers, it is factorable with imaginary numbers. And I found that out by taking this parentheses here, setting it equal to 0 and solving, getting my zeros, and then back substituting them in like I did with the negative 1 here. I knew negative 1 was a 0, and so I put an x positive 1 here. Okay, I hope all of that makes sense, guys. Alright, I hope this video's been a help to you guys. If you have any questions, don't hesitate to call or email.